Okay, uh, so today I would like to talk about the challenges in training and optimizing generative AI models and how we are working to automate this process. This will be quite a bit of a different talk, but I hope you will enjoy it nonetheless. I am Ehud Barnea. I head the AI task at AI, and this is something we are now working on. So the world of generative AI did not skip on retail when we have three main applications. We have the generation of product backgrounds that are supposed to increase sales, and it's only about backgrounds, but also add text and so on. In the world of virtual try-on, you can try out different clothes or furniture at our home. In product ads, we generate entire scenes with the products in different poses and so on. And in all of these, it's super important to preserve the identity of the product. We can change the lighting, and we need to, but we cannot add any bit of color to change how the product actually looks like. So a different title for this talk could be, what could we do with a model, or what could we do with an accurate but slower model? Now, how did you get about to working on this? So Task AI is a small startup in Tel Aviv that was started about 5 years ago. And the main product was about annotation based on a specific kind of crowd, that instead of people that come and do work for money, like in Mechanical Turk, we tapped into random people that want to consume digital content, such as a song or a skin in some video game. And instead of paying, they're given the option to do different kinds of tasks. So the normal one is to watch an advertisement video. And in this case, we give them annotation tasks. So it turns out that when you build the crowd this way, you can actually turn it into a process that is automatic and with a known SLA and with accuracy that doesn't drop over time. So this is what the company built. It's the main product. And now I recently joined to see what we can do with it. That is not just standard annotation. And what we are doing now is trying to enable the generative AI evaluation in order to enable it to have a rapid optimization of models. So in general, we are trying to make the generative AI research feel more like discriminative AI. So we set out to do standard evaluation, but along the way, we discovered more unexpected challenges, and I would like to take you on this journey. So the initial problem is that when we develop a standard machine learning model, we have a cycle of we try something and we measure it, and we try and we measure it, and like that we train again and again, fine-tune parameters until we have something that's hopefully good enough. Now, in generative AI, we don't have the measure part. So we try something and we look and we try and we look and we just look at a whole lot of results to understand what's going on with our models. And it can be quite problematic for research, especially for optimization, where we need to do it just too many times. So when we want to evaluate or just think about how good a generated image is, it has to be good in several different aspects. So a generated image should match the prompts. It should be aesthetic or just to look well, depending on who you ask. It should have no defects or hopefully just a few defects. It has to preserve the identity of the product or the fit. So if you generate an image of a high-rise jeans, you can't draw it to sit on a person like it's a low-rise jeans. When we fine-tune a model on client's data set, then you also need to create images that fit this artistic style, and so on and so forth. So there are probably about 7 different use cases, and this is more about image to text. Now, first challenge that we saw arising from this point is that evaluation done by yourself just gets quite confusing. So when we talk to generative AI researchers, they say things like that. So I like to look at things like prompt following and aesthetics and defects and so on. I look at this, I look at that, and I try to understand what's going on. And there is no one way to reason about this. So it's quite confusing. Other people say maybe the most important measure is usually defects, but not always. And one research manager actually said something like, my researchers shouldn't even make this decision. She doesn't think it's right that the person optimizing the models would try to understand how good it is. So it appears to be quite confusing to account for all of those different measures into one decision. A second kind of challenge is uncertainty or unease that people often get because of the subjectivity of the problem. So when a single researcher looks at an image, usually they would say things like, I think that blah, 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 but I'm not so sure, or I want to see if the annotators agree with me, be it like specialized annotators or just normal people. And what we often also see is that the whole company tends to be involved in this process. So people upload images to Slack channels, or they have meetings internally, and you have researchers and product managers and designers and CEOs and CTOs, everyone looking at the images, trying to understand what's going on. But when you're a single researcher or a single product manager, you look at an image and sometimes you're not sure and you're just uncertain about it. And this causes unease that people look for different ways to feel okay about it. So those two challenges that we discovered when we started working are a bit different in nature. They are not AI challenges, but they are more of a human issues. But those human issues can also be improved. Now, a third challenge is in accuracy. So basically any application that we have, in my opinion, has some sort of underlying accuracy. Now, when I talk to generative AI researchers and I say the word accuracy, usually they don't really like it because you look at an image and it can be good, can be better. What does it even mean to have accuracy? And I think it's more of the thinking you develop when you work on foundation models. But when you work on actual applications, there always has to be some sort of is good enough ratio that you would have to keep. So in normal shelf understanding, for example, in physical retail, not generative AI, it's already quite known to researchers and to even customers that you need about 95% accuracy in your product recognition. And if you have less than that, you just have no product. And when it comes to image generation, it appears to be usually a bit of a smaller number, usually around 20 to 25%, because the generation process nowadays, at least as it seems in most cases, is more of a guided process where you have the user that's a user of the system. And so you don't have to have a single image that works good enough. You can actually generate 4 or 5 images and let the user choose from this. So even in this kind of setting, there is some notion of is good enough for the user. So there is accuracy, right? So when you train generative AI models, hopefully you train it once or twice and it's just good enough. But if it's not good enough, then you have to go through the normal grind of optimizing models, improving your data, finding better parameters, and so on. And the problem is that without proper evaluation, it's very hard to do the whole optimization phase, where in one training you have many different checkpoints, and you just cannot look at all of them. And also when you train a model many times, it also becomes hard. So when I was working on this kind of problem for product recognition, I trained just a standard model about 250 times just to find the right type of parameters. Now, it just cannot be done when you have to look at results all the time. So when you train a model, you take a bunch of images, you write captions for these images nowadays, even automatically, and you start your training and you see this kind of loss. Now, the problem with this loss, especially in image generation, is that it's very far from the qualities that you actually care about. So looking at this curve, you still don't know when to stop training, and you don't know how to find the best checkpoints without just looking at it. So we want to be able to help, especially in those 2 points. Right. So eventually we want to have a curve that looks a bit more like the one on the right, where you have the quality metric you care about, and you want to see it improving, you want to see it saturating, and so on. But to do that, we need rapid evaluations for each and every checkpoint, or for most of them. So you could try and use human annotators that you hire, but they are not really available when you're training a model. I mean, you can use them every now and then, or every few days, but not while training. And you might want to try and use models as judges, which has become quite popular in LLMs, because they're better than those in computer vision, but still those are unreliable and they're highly biased, and won't get into that now. So a possible solution that I would like you to know about is that using crowds automatically. And I talked to some people, if you don't know how it works, it can be, it can take time to understand how to make it work. So I want to tell you that it's not so difficult. So what we call human as a model. So essentially, when you use crowds, you're able to ask a question, and once you know how to ask it, you essentially get an API that has high accuracy, stable accuracy. It can be fast-ish, and it will be cheaper than hiring actual annotators. And it has more nice properties where if you ask many people the same question, then you can overcome the objectivity, and you can overcome some of the biases by asking different cultures, different languages, and so on. So basically, you want to use the crowd in order to create this kind of API that just feels like a model. So very briefly, how is it done? Now, there are different crowd solutions. I don't really know all of them, but this is how it works at task. So generally, you get a bunch of people to ask a question, and they undergo this Duolingo-like session, where first you ask them a bunch of training and testing questions in purple, and those teach the person to do the work, but also test them to see if it's good enough. So after a bit of those, you filter out those that are not capable of doing the work or just don't want to do the work, and you're left with a smaller bunch that answers accurately. Now, once you have that, you ask a bunch of actual questions in orange, and every now and then you ask testing questions. So they know they're being tested, and also just to make sure accuracy doesn't drop over time. And if you set it up correctly, it's very automatic and very nice. Okay, so we set up this kind of crowd, and we wanted to see if we can use it in order to evaluate the different properties in image generation. So first we wanted to try to Likert it, and we didn't really think it will work because we saw it on ourselves. But basically, we wanted to try and create this learning curve over time. So we took 20 prompts and 3 seeds for each prompt. We generated images for those. And each of those images, we asked 30 different workers. Now, we asked 3 questions. We asked about aesthetics, defects, and prompt alignment. How much good is it from 9 to 5? So here in this dragon example, it can be quite aesthetic, but it has the leg defect, having 3 or 4 legs, which is not supposed to have. So basically, we ask people to rate images according to that. And we saw that it doesn't really work because when you have 2 models that are from different checkpoints, the results are very similar. So it's very hard to tell them apart on a 1 to 5 scale. So just to see a bit of results, on the left, we have aesthetics. On the right, we have prompt alignment. Where on the x-axis, we have different checkpoints. And on the y-axis is the value between 1 and 5. And the yellow triangles show the mean of the answers of the users. And the box shows the different quantiles. So as you can see, the difference between the means is not substantial in relation to the size of the quantiles or the distribution. Prompt alignment looks quite the same way. So we can see that the model is much better on prompt alignment than on aesthetics, but in this case, inside each measure, it's just not fine-grained enough. So what do people do when they want to compare things that are more similar? Well, they use comparison. So in this case, we can see two different answers. And on the left, we have an aesthetic dragon with no defects. On the right, it does. So when you ask people which one is better, it becomes much simpler. So we did this kind of experiment. We ran this training of the model, and basically for each checkpoint, we checked if it's better than the one before it. And if we have, let's say, 100 images, anytime the new checkpoint is better than the previous one on an image, it gets a point. If it's worse, it gets a minus point. And if it's kind of the same, it just gets 0. And we got this graph on the right. So the first one, 500, is just initialization. It's not a real value. And we can see that checkpoint 1000 is better than 500 in almost 50% of the cases. And then in 2000, it's better than 1000 in about 30% of the cases. And then it drops a bit below 0. And so it continues, and it might look like this is a converging graph or something, but actually we have a problem here, because when we compare each checkpoint to the one before it, we don't really know how it is in relation to the one 2 before it or 5 before it. And this doesn't really enable us to understand what is the best checkpoint or when we converged. So what we do instead of that is a bit of a smarter process, where we go over the checkpoints. When we start with the first checkpoint, we say this is the current best. And then when we have a new checkpoint, we always compare it to the current best. If it's better in a statistically significant way, then we jump over to it and say this is our current best. So here on the left, you can see that we start with a star. We compare everything to it. Then 2000, just an illustration not connected to the graph on the right. So 2000 is also a best one, so it's now our current best. And all the next ones are not better than 2000. So after a while, we can stop. So just to make it look a bit nicer, on the right, we can see the p-value in checking whether one checkpoint is better than the best one. And you can see that below the red line of 0.05, we say that it's significantly better. So basically, anytime we saw a point below the red line, we say, okay, this is our current best, and we work with that. And at some point, the values would saturate, and then it could stop. Just to say it, because it's a p-value, most of the values are much higher than 0.1, but it was flipped just to show the graph in this case. So basically, we are trying to use this evaluation in order to solve the different challenges in this domain, where if evaluation is confusing many of different measures, and now once you measure actually all of the metrics, it becomes much simpler to reason about them, to connect them all to have one metric. And again, for the subjectivity, when you have something subjective, it's subjective for one person. But if you ask many people and you understand the distribution, the mean and the variance, then it became objective and something that you can work with without uncertainty. And finally, the first point was that it was how to optimize when you look at different checkpoints and so on. So an automatic evaluation solved that. Let me add just one more point that I think is interesting, is that usually people don't really need any automatic evaluation when they're just starting, because it's easy to see when your model is really bad and when it's improving. But once your model is good enough, and then you start to optimize it more and more, this is when it becomes much more crucial. So in general, CRUD enables automatic evaluation, and then both AI problems and human issues become simpler. And Task, we are now developing this evaluation as a SaaS-like solution. We are partnered with one leader in generative AI, and we are looking for more design partners. So if you happen to be working on generative AI at the stage where you need to optimize further, then we'd love to try and help you out, guys. So if you just want to play around with evaluating images for yourselves, you can go to this website and just look at it and try to ask yourselves, is it more aesthetic? What about the defects? Is it good enough? And so on. Okay. Thank you. Questions? Okay. And now we have Kobe. Yeah. מה שלחתי? פה יש את ה-HDMI. אני זוכר אם שלחתי לך את זה באימייל העבודה או באימייל ההפצי. לא יכול לעבוד. רגע שנייה, אולי זה נפסידו. זה נראה אם הוא רואה את המיקרופון. קיבלת המיקרופון? הוא בסדר? הוא גם לא ראה אותו משום מה במק, ודווקא בלורקים נראה שזה היה בסדר. טוב, לא עכשיו. כן, נשתף מסך.
Hey. Okay, thanks for being here. My name is Kobe, and I'm introducing the large-scale product recognition we do, specifically to improve the ad performance. So imagine you are an advertiser and you want to run an ad campaign. What you usually do is create a static ad. You would carefully curate the image, the text. You will set the ad landing destination to your website, and you publish the ad. Then all users are going to see the same ad and hopefully convert. However, a much more performant ad format is dynamic ads. In dynamic ads, you upload many products and set the landing destination of each product to the product page on your website. Then you publish the ad, and the order of the products is personalized per user. When they click on the shop now, they are going to land on the product page, where they are more likely to convert. The problem is that although dynamic ads are much more performant, most advertisers choose to run static ads. We think that the reason is that they have much more control over their brand. So they can choose the image very carefully to show their brand, the text, and overall it's a more standard ad. So the question is how we can make static ads perform as good as dynamic ads, but still preserving the brand of the advertisers. And the solution we think is product recognition for product-aware ads, so that we are aware of the product ID in static ad. Let's see some ad format that aligns with that. So the first format is ads with product tag. In the ad creation phase, the advertiser are shown recommendation to what product to tag. They have full control over the tagged product. They can opt in, opt out, override the recommendation, and then they can publish the ad. In the ad impression stage, when buyers click on the tagged product, they are landing on the product page, where they are much more likely to convert. So this is much better at the landing destination. And here we need to have like a very high precision for the recognized products because we don't want to break the trust of the advertisers. Another format is product extension. So here advertisers are opt into the format, but they don't have control over the shown products. The products are personalized per user. And once a user click on the product below, you can see there is a carousel. They are landing on the product page, as you can see. Here, the product recognition precision is not that important. Even similar product do the trick. Also, latency can be very high because everything is done offline. Another interesting ad format is the destination optimization. So advertisers are going to opt in to the format, and the ad destination is going to be personalized per buyer. And one of the possible destination is the product page that we recognized in the creative. Here also advertisers don't have full control of which users is going to land where. What we saw from the experiments that users that are more high intent, like are more likely to purchase, are going to land on the product page, and users that are like in the exploration phase are going to land on the advertiser storefront. Another use case for product recognition that I don't have a slide for is a feature for the recommender system. When we input the recommender system, the product ID, we can share signals between dynamic ads and static ads for better recommendations. Okay, I hope I managed to motivate you that product recognition is important. So let's see how we do it. Basically, we follow like a common paradigm for search. We have the ad. We run object detection to detect commercial objects. Then we extract embeddings of the product. We are querying a vector index to retrieve products. And then we run product ranker, like with more sophisticated features, to have the final list of products that we believe are in the ad with a score of the confidence that are shown in the ad. So let's talk how we build the index, the vector retrieval. So the first and foremost data source is the dynamic ad catalogs, where sellers upload their products. However, this is not enough because the product is not always contains like the full details, like many images might be missing, the price, the availability status, and also not all products are uploaded to databases. So we are missing many of the advertiser products. What we do to overcome it is we crawl the website. So we are sourcing all the advertiser products from the website and upload them to our database. For high revenue advertiser, we are doing it about once a week to update the availability status or maybe like adding more images. Once we have all the products, we are indexing them in a vector index. So basically, we detect the most prominent object in the product image. Extract embeddings. You see that the embeddings are quantized like in bits because we want to save storage and we want a fast retrieval because Amic distance is cheaper than Euclidean distance. So in the index entry, we have products and their main image embeddings, right? And we train a KNN model on top of it for faster retrieval. The index size is about 10 billion products. This is the scale we are working with. So a few words about the embeddings. So we use ShopNet. ShopNet was developed by a startup that Meta acquired. Basically, we minimize the embedding distance between in the wild product image and the product catalog image, which are quite different. And the embeddings are quantized at the training stage to get better results. A few cool details from the paper is that they used the active learning approach because labeling of images with the product ID is very expensive. So there is such iterative process where they train a model, then extract features, did the matching annotated, and then repeated the process over and over. And also they use the marketplace queries to have a data set of product and attributes. So the process was like as follows: the user search for a red dress, user click on the product, he reached for the contact, reached for the seller responded is available or not, and then they recorded the data set. Unfortunately, we can't use such data anymore because of regularization constraints, so the next ShopNet should be trained without it. Even though the embeddings are quantized and we use only dynamic, even if the quantized, we still can cover all dynamic edge products. So we are looking only on the top 90% revenue advertisers. And for that, we get 10 billion products. And similar to other e-commerce data, there is a long tail of many advertisers with small revenue. Good. So now that we have the index, let's see what it means to do inference of such product recognition. We first found a quick hack. We saw that many advertisers set the added landing destination to the product page as we sourced it from the advertiser website. So we can have high confidence by simply match the URLs of the ad and the products. And then we don't need to apply any models and the planet is happy. In case this is not the case, we need to apply the object detection that detects the commercial objects and extract the ShopNet embeddings. Then we query the vector index. The vector index returns a list of products. Here it's interesting to see that we applied the advertiser catalog constraint. So we don't search in the entire index. We search only in the advertiser catalogs. We saw many problems where there are use cases that we need to search in the entire vector index. And we saw many problems. For example, there are many advertisers that sell the same shoe, like Nike shoe. And it's hard to understand who is the Nike official seller. And also there is a brand safety issue. Let's say we search for a Nike shoe and come up with a Nike fake product. So this is undesired and it is still an open issue for us. After we achieve product, we apply the product ranking where we use more sophisticated features. We use a simple model like GPUs because we want to run it in scale. And it's a binary classifier, is the product is shown in the ad. Features we found useful are features that compare the product attributes to the ad attributes. For example, the distance between the embeddings, the distance between the product image and the ad media embeddings, whether the name of the product was shown in the ad creative and things like that. We also use the ad length destination as additional features. Another feature we care about is the dominant products. Let's say we found a product, how dominant it is in the media. So there is a big difference if the ad was showcases a single product, and then we can set the ad length destination to this product, as opposite to multiple products in the ad, where we more where like ad format as product extension is more relevant, where we show many products in the bottom of the ad. So we applied a simple heuristic that takes into account the bounding box size and how centered the bounding box is, and for video the product frequency along the video. Since we run it in scale, it's very important for us to understand where are the bottlenecks. Basically, given an ad, let's say it's a video ad, we extract in average 13 frames. So we need to run the object detector and embeddings extractor about 13 times per ad. The object detector detects 10 products in average. So we need to query the vector index 130 times per ad. The vector index returns 15 products per bounding box. So the product ranking should run in roughly 2K QPS. Some of the future work of product recognition in Meta, we are collaborating with Ray-Ban. Ray-Ban introduced like smart glasses with Meta. And a common question is, tell me about the brand of this kettle. What we do, we apply the product recognition for the image that is captured by Ray-Ban, and the product information is then propagated to a reg system that provides the answer for the user. We are also looking to expand the product recognition to social media, social content. The problem is that user-generated content is much larger scale than ads. So we think about applying a lightweight commercial classifier to understand whether we should run the product recognition. And there is a tragic canonical product, let's say before, like the shoes, the Nike shoes versus a different brand shoes. And the product retrieval has become much more expensive since we search in the entire vector index and not just in the advertiser catalog. And there are regulatory concerns where we should enable opt-out of users that don't want to be part of it. Some issues we found with the product recognition is that it underperforming for beauty products. For example, in many beauty ads, the product is not shown. What we see is just like a woman that is wearing makeup and discuss about it and not actually present the product. And currently we only retrieve product by their visual features. So by expanding to more modalities like text and speech, we can be more accurate. Next.
Good question. So I think this question pertains to the underperforming and beauty products point you have here, but have you considered using a foundation model like segment anything to more precisely down, the objects in order to produce those vector embeddings?
Yeah, actually we tried it. It performed not as well as the object detection and ShopNet embeddings. I guess because ShopNet was not trained on the images of that was segmented. So yeah, it performed basically that.
Thank you for the great part. I want to learn about the product dominance and how you come up with the scope of that, implementation, the size of the box.
Yeah, it's basically a function of the location and the size of the box. Exactly, like there is some kind of heuristic that weights both of them, and then we apply a softmax function. So if there is just one product, it not matters where it is in the image. It gets the score of 1. But if there are several products, the score is summed to 1, and it depends, like each bounding box depends on the location. And this is valid only for images. So for videos, you have a different type.
You mentioned that you are using the KNN to threshold out the outliers or find the ones which are close to the user's actual. But do you choose, like, do you have a hard number that needs to be like close by this threshold, or because there might be a very big cluster for some products and there might be a very sparse vector somewhere else? How do you know where does it lie, and how do you, is there a dynamic thing choosing between the thresholds of the KNN?
So basically, the KNN is used for faster retrieval. So we take the query embeddings, right? And we compare it to the KNN centroid. We find like the top 10, the top closest centroid, and then we are searching just inside these clusters.
The father, you find the most prominent image of the father as use that to basically then how would you detect what is the most prominent image?
So it's come back to the dominant product. It's the same heuristic, just the largest and most centralized product, basically. Yeah.
Do you ever have issues where the object detector is splitting out an object into several separate items whereas it's supposed to be one?
Yes, so basically, like we saw some issues that the object detect like the shirt and also like a small pattern like inside. For it, it's not that of an issue because we research both of them. So and then in the rank it's going to be solved. And here the product image, basically like the most common product image is just the product on a white background. It's even simpler than this, so it's not really prominent.
Can you tell me something about copyright of the product or privacy issues on systems like that? If there are any.
Yeah, so like I'm not a big expert in this, but I guess like when an advertiser runs a campaign, they're going to sign like many forms. So I guess one of these that we can call their website.
Could you go to the last slide and talk a bit more about your challenges, part of like embeddings and encoders and text of the product itself? Do you also embed that? And do you face any challenges with that?
Yeah, so currently we only index the image, right? So we have only visual embeddings. Sure. Much more like a much more better way is to have like product embedding that takes into account the name, description, images, rating, like when we saw like in the first presentation of the day. There is, I think someone is working on it in Meta, but it's not like close to production.
Thanks for the talk. Are you using like reviews anywhere to kind of like insert this out, further personalize and say, okay, this person probably even more aligned to these kind of reviews and they use that.
Yeah, so when we detect the product, we like in this format, we pass it to our recommender system, and the recommender system takes like multiple signals, also reviews, rating, and all, and then it personalizes it. So this is like the product recognition just fed to the recommender system.
Okay. How do you deal with the auto-distribution and similar items?
Similar items is just a matter of the ranking score, taking like lower thresholds, enabling lower precision but high record. Regarding out of this distribution, I didn't understand.
Items that the model
yeah, I guess like it's part of the metrics that we track, like recall and precision.
Okay, let's thank the speaker.
is already.
Sorry?
The Zoom is already available.
Yes, but we need to put the computer here because in almost all of the talks, the face is something like.
Can I plug? So,
Yeah, and let's see if it recognizes the speaker.
sorry?
Can you press the arrow button? See, no, it doesn't really recognize the speaker. Oh, it's turned on. Never mind, computer is good enough. Okay, yeah, so just share the screen.
You mean they cannot hear?
No, they can hear you just via the microphone from the computer.
Oh, okay.
But it should be good enough, especially if it's a Mac. Okay, I just want to put it a little more.
I can show the
No.
complete desktop, I guess.
Yeah, all set.
Okay, so good afternoon. Thanks for being here. Thanks for the invitation from the organizer, Marina, and the others. I am Roberto Pierdica. I'm a researcher at the University Polytechnic of Marche. I am an architect and engineer, so I hope to meet your expectations, even if I will not talk directly of retail, but I will make a bit of change of domain between what I prefer to do, that is taking care of cultural heritage in my life, but I have been working in retail for a lot of years. So I will tell you something about my first 10 years of career working in a multidisciplinary group. That is the one that you see here. The name is VRAI, Vision, Robotics, and Artificial Intelligence. And the group works in a lot of domains, like I told you, cultural heritage, agriculture, computer vision, of course, AI, and even retail. And I was one of the founder of the group from 2012, but I was not an AI guy, an informatics. But the vision of my supervisor told an architect to go into the AI domain. So you will see what happened in the upcoming years. But basically, I am a geomatics. I don't know who about you knows about geomatics. Is the discipline that takes measures. And if you see my group now, the name is Geomatics Applications and Processing. I have a lot of patients like dogs, moto, archaeology, of course, and a lot of other patients that I cannot tell you here. But what I do is taking measures. So during the years, we witness a lot of needs in the retail domain, most of them related with measurement. I generally take measures to recreate the 3D models, to map inconsistencies in the facade of buildings, to create building information modelings, and so on. So using such instruments, depending on the size of the objects and on the quality of the reconstruction that we want to achieve, we use different sensors from photogrammetry, remote sensing, laser scanners, and so on. And when they asked me to do this talk here, I was wondering which can be the contribution, the vision that I can give to these domains, since it's not mine. And when I start working in the informatics community, I was understanding that, in my opinion, these three pillars are the most important for the retail environment. The first one is the physical space knowledge. What does it mean? It means translating into information the space in which we live. and developing algorithms to understand what's surrounding us in terms of 3D data is such a complex task. The second one is understanding the human behavior and measuring what people do inside the space. That can be a retail environment or an archaeological area. It doesn't care, it doesn't matter. And the third one is what people do in a virtual environment. And after COVID, we have witnessed a very, very change in which people experience the space and so on. And there is the new paradigm of a digital twin or a phygital space. That means translating what people do in a real space, translating it into a virtual environment. So I went through different definitions from the literature, starting from a very, very recent talk made by Fei that Marina suggested me before this talk. I could not take inspiration from Fei, of course. I have neither a nail of her, but okay. I found very, very interesting what she was talking about space intelligence. That can mean everything. The ability to process visual data, and we know that are not just visual data, they can be a lot of kind of data. Geospatial intelligence, that is my discipline, even monitoring what happens in our Earth from satellites and everything. The semantic understanding, that means giving a meaning to what we have around us. And the knowledge representation, that is almost the same, but using knowledge graph to represent the space. And the concept of digital twin, that in my opinion in retail would be really, really important, because digital twins in the construction site is a state-of-the-art application. So the life cycle of what happens inside the building doesn't take care about people inside it. That should be, we construct building for people, and it's sort of strange. So I went through what we did in this year. So I will tell you the stories that we developed on the cultural heritage domain and how we moved and translated into the retail domain. At least I will try to do that. So a bit of history about understanding the surrounding. We have a lot of definition, but basically the three main important application that we can have into a space when we translate the space from the continuum to the discrete data that are the point clouds is the classification, the part segmentation, and the semantic segmentation. That seems to be the same things, but it is not, because it depends on what we want to do with such data. And at the different scales, from the city to the indoor environment, is a task that is fundamental. And we have seen the previous talk when there was the store mapping, but including even the interpretation of the space can be really, really important. What we did was to use a lot of the human efforts to label data, because if it is difficult to label data into the images, you cannot figure out how it can be consuming to do it into 3D. So we took a lot of 3D data from the cultural heritage domain. We presented this challenging data set into CVPR 2009, 12, 20. Yes, there was the World Championship. Yeah, I remember now. And we proposed this data set to the community, but we didn't find something similar to the retail industry. Maybe because it is changing in a very abrupt way. I don't know, but it was really an effort, and I claim, even if there is the importance to create a sort of data set like the one that we did for the cultural heritage, because it emerged a lot of interesting things when performing semantic segmentation of point cloud. Because in our domain, it is important to give a meaning to the structures of churches or buildings, because we have to transform it into building information modelings to provide restorers and other people dealing with the cultural heritage fabrica to perform the BIM, so putting information into the 3D models. But there are a lot of difference in terms of how many point clouds that can be in a class with respect to another. So what we did was to try to make the same thing into the retail environment. Before, I wanted to ask, in the retail, is there the need to have so high accuracy? Because, okay, the cost of such instruments that can collect with mobile mapping a lot of data are quite high. But if we can store more data of store, sorry for the game of words, in few times, and we can collect data to label and to transform into classes inside the store, maybe it can be useful. From our task, we use the PointNet++ and other very well-known networks from the state of the art. We went out with quite good precision for some classes, but as soon as we increase the number of classes into the retail, of course, the classification accuracy reduce. But because we had no data, we had not labeled data, and a promising thing it can be, if it is useful for the retail environment, to understand if there can be a benchmark data set to collect and making the classification, to perform the understanding of an environment, of a retail space. About human behavior understanding, well, during my PhD path, we coined this term that was sensible spaces, understanding what people do inside a space to provide information to them, and at the same time to collect information about them. So it was a bidirectional exchange of information, because as I understand during this whole day of workshop, customer profiling until analytics of the users, attracting user to do something when we monitor what they do is important. Then there are quite a lot of technology already available. When we started in 2015, as far as I remember, we were calling space intelligence and using proximity technology to provide the user. Maybe most of you knows about the use of beacons, that are those Bluetooth low energy systems that at the same time can track the user behavior and can provide notifications and stuff like that to cluster what the people could do. And in that case, what we did was to merge the RGB cameras to detect the passage of people in a certain point, and then to track their movement in indoor space. I remember that I am geomatic, so I love to take measures, and with GPS outside is really easier nowadays to do that. So what we did was to translate this concept of sensible space even in other domains. For instance, in outdoor spaces, generally retail is something more related to brick and mortar space and closed space, physical space, but it can be done even in outside spaces, even to understand the mission of a place, to provide the decision makers with the more aware processing of design, to redesign a place that cannot be just a closed space, but even an open space like a park. What we developed here was a mobile-based application on the concept of sensible spaces within an European project called Cyberpark, to understand the impact of information and communication technologies on the people. But at the same time, what we did again was to track their movements and understand their behavior, to try to perform a clustering about what people prefer to do in a park, like running rather than going to the cultural heritage sites and so on. And afterwards, what went to our mind was okay, we collected a lot of data, but can we predict what people do in a place? So here you can see different ways in which we tried to perform this kind of stuff, from the clustering of the user to the prediction of their path and of their movement. And we did at another different scale, that is the city space. Here, if you want to detail, you can see our publication in +1 that we did with Marina a few years ago, using floating car data. So it doesn't matter the scale of representation in which we are working. We will talk about it at the end of the presentation. We need specialized applications to understand the specific needs of the domain. And back again, we tried to apply all this concept into the museums environment, putting a different hotspoint to detect with different technologies what people do, their preferences, because I found that there are a lot of correlations between the two environments. Even the museum environment, in a sense, can be seen as a retail environment. If someone listened this thing that I told, maybe can be angry, but okay, this is another story. Because if you go inside a museum, you cannot think to visit all the paintings that are inside. It's like going inside a library and reading all the books is like sort of impossible. So driving the people within the space and putting them according to their preference, sending them according to their preference in the specific place is something that is really fascinating to me, like a passion of art. So here is the design of the application, and this application we called MEMUS, Measure Your Museums. And finally, what we got was the collection of all the data with all the indicators that I guess are used even in the retail environment, like how many people stop in a place, if they interact in groups, and other things that maybe you know better than me. And the same could be done into the retail environment. Here you can see one of our main applications that we did with ultra wideband, collecting a lot of data from different stores. There you can see the number of data collected and the possible path that people could do. And again, that in my opinion, that's the most important thing nowadays, using generative networks and LSTM methodologies to try to predict the trajectory that people do, and in that way, maybe my rule that I like a designer to optimize the layout according to the preference of people inside a store or a museum or a park or whatever. Okay, the third pillar, maybe the one that I love the most, because virtual reality is one of my discipline and one of my domain. From a lot of studies and from an European project, XR for All, was born Deep Reality, that is a company, a startup dealing with the stuff that you see, artificial intelligence, augmented virtual and extended reality. And the idea of the company was really simple. If with our eyes we are able to detect everything quite easy, to detect what's inside the space, it is not so easy for a smartphone or for a system. And in the retail and in the museum space, these systems are still struggling. Please correct me if I am wrong. But as far as I know, if I go to a superintendent and I say I want to develop an application that detects everything inside the museum, they say, okay, they close the door and they send me away. Because there are a bit of skepticism with the technologies that substitute the guides and so on. I don't know in the retail domain, but I think it's the same. So the idea was to merge artificial intelligence from one side and the technology already existing, like augmented reality, from the other, and put them together to understand how we can improve. Because another bottleneck is the content creation, and we have seen before, we do the generation of content today is quite easy. So that's the reason of my talk. Are we running behind technology? Because when this project was run, there was nothing of what we are talking these days in CVPR. And the application that we developed was just to feeding the camera stream and to recognize and trying to understand from the mobile phone what the phone was looking at and recognizing the object. It was not so easy few years ago, because the foundation of augmented reality that were already existing had not artificial intelligence embedded, so systems like Unity, 3D environment. It was really, really difficult. And the other problem to include in mobile devices, artificial intelligence, was that they are very, very time consuming. So pruning neural networks to work into the mobile devices was not so easy at all. But we tried to do that. We developed this architecture to allow the model to recognize everything from the space, to understand and to give the phone the knowledge of the space using out-of-the-shelf devices. And finally, we got the application that you see just a couple of years ago, with very, very good results, because again, tracking with augmented reality was using QR code until 5 years ago, but it could not be possible to put a QR code in the face of Mona Lisa. So using detection of objects without anything was quite cool, and projecting in 3D the result of the tracking was not so easy. But again, we were beaten by Google, and 2 years later everything was done. I don't know if you have seen something about the project Astra, that with just millisecond is able to recognize everything inside a scene and to take notes and make annotation about what's inside the space. And for me, it was quite impressive. And I was saying, okay, I'm running behind technology because we invented something, but with very, very few time of life in front. But okay, we can even exploit these kind of applications. Another thing that for me is quite important, like a geomatic, don't remember that I am a geomatic guy and I love to take measure, is to understand which data are important inside the space. Maybe you know about Matterport, that is one of the main tools that can be used inside a store. But I didn't hear about using NeRF and omnidirectional cameras. And a few days ago, I was in LinkedIn and I saw a post saying that this is something that will delete from the from the market Matterport. I don't know if it will happen, but this was done with the neural radiance field in a few minutes, I guess. Yeah, just collecting with a GoPro. And again, even the issue of the costs, in my opinion, here are going to be neglected in the future, because just with a camera that costs like $300, we can have everything. I have to see and to check if this model below can be measurable in a sense. I don't know. Maybe you know, and we can discuss. What we are working now. Since our company is even working on virtual tours for education, and I was going into different educational companies and into videos performing education to the clerks of groceries like that. And one of the questions they gave us was, we take a lot of time to develop all the content and to create virtual tours of an environment, because we have to get inside the store, we have to get the permission, there are a lot of people, we have to stop the store and so on. So we went through quite Googling in a few minutes, and we are including in our platform that is called Inside Deep if you want to have a check. And we just have to put very, very short prompt, like we did it yesterday with Marina into the conference hall, and we wrote retail environment with grocery store and la la la. And what we get in output is a complete virtual tour of a store. And in my opinion, quite impressive, because there is not more the need to go inside the store to create a virtual experience of a retail environment. Finally, and I'm going to close my talk, even if we are in time, I think. We are trying to introduce 3D models into the panoramic images, but another very, very important thing, in my opinion, is not just to understand what people do inside the real space, but even to understand what people do into the virtual environment and in virtual tours. So we developed this workflow with the idea of detecting if the point of interest that we want people go to see are exactly what people go to see inside the virtual tour. And we had sort of surprises. First of all, because it was not easy to develop a system that with the right coordinates inside the virtual tour can be able to detect exactly where people focus, where people look, because otherwise you have to use eye tracking, but okay, you cannot say all the people that visit a virtual tour to use an eye tracking. So our system is able to understand where people look inside a virtual tour, how much time they spend, if there is a revisit of a panoramic image. And here you see, of course, I will not go through the statistics, but these are real data collected by 100 more users, and it's clear that the trends are depending on the masterpieces that are inside the museum. I can perfectly understand that the retail is different, but if we wanted to understand in which product into a virtual environment people are interested, maybe we can just use a virtual tour rather than creating the bomb of 3D model that we know how much time does it takes. And finally, a paper that we are going to present in another conference in Italy is to develop a LLM-guided virtual tour experience. So basically asking the virtual tour to bring the user when he wants to be brought. So if you can see there, we just created a simple JavaScript prompt with the coordinates and with the prompt. Here we use OpenAI API to ask the system, can you bring me in the painting with I don't know, 2 people, or with green, or a painting where the name Antonio appears, or whatever inside the virtual tour, and the tour is able to, among the, here we are talking about 40 or 50 images. Of course, I cannot show you everyone, but this is a virtual tour of a very complex museum environment with like 25, 30 tours, maybe more. And the user can just write according to his preference when he wants to be brought, and the system directly bring it into the point of interest he is searching for. So the idea could be, why don't using this tool like LLM-based virtual tour driven into the retail environment? This is, of course, a mock-up, but now that we have the knowledge of the space, and now that we have the knowledge of what the people and users do inside the space, why cannot we bring into the virtual environment to provide a virtual personalized customer experience into the retail environment? So this is what I was thinking to prepare this talk that is going to the end. And these are, to recap, the 3 pillars that we were talking about: the physical space, the human behavior understanding, and the virtual space. And sorry, what's next? I was just making some consideration, even looking. I'm lucky because I'm the last one of the series of talks, so I get a lot of insight from you. I think that providing personalized virtual experience is quite easy nowadays. There are the tools to do that. I don't know, but again, please tell me if I'm mistaken, but virtual tours and virtual reality in general in retail is not something used, but I think it can be useful. In my opinion, the main constraint and the main bottleneck is that it's difficult, and we have to spend a lot of money to create personalized virtual tours in museums. And another thing I would like to push is, from one side, we are developing low-cost tool to map the store, but at the same time, we need the very, very detailed mapping of the store and the knowledge of the store, and creating semantic segmentation. So we should find the balance between accuracy and what we want to get out for reaching out the right knowledge of the store. And even understanding which is the reason, because one of our guide in artificial intelligence say that even humans are specialized. So why don't we have to specialize the algorithms to do what we want in the specific domain? And this is an open question. The other open question is the funny discussion between Elon Musk and Yann LeCun, each one saying the other that academia is more important than business, and vice versa. I of course don't have the answer to this. I'm here representing both souls, and I am open to the debate and to the discussion, and I really want to thank you for your attention.
Has your company started working with retail?
Not yet.
But it's
Looking like? Why not? My company is now dealing with schools, educational applications for a younger generation, like using ChatGPT and virtual tours for education. But I've seen a lot of application in even training into retail for the store clerks, and so yes, I would like to be interesting. Very, very good question. Are you a retailer? Cluster would be enough. Yeah. I am before I am a designer. So for me, like if one person say, okay, I have this cluster of person, your layout is like this, and I want to change it, for me cluster would be enough. But it's changing. Maybe one of the path even design is changed, that is that even the space has to change rapidly. So trying to forecast not what happens now, but forecasting what can happen in the future. And even because we see that in retail's environment are not as static like museums. If you go in Louvre Museum, is the same like 30 years ago. But I think if you go in a retail store tomorrow, you will not find biscuits like you did yesterday. So maybe prediction can help in making more dynamic design of a space. But it's just my idea. I was not prepared for this question. I hope my vision was fine.
Okay, so thank you very much.
Thank you.
Good afternoon, everybody. My name is Austin Groner. I'm an applied scientist with the Amazon Easy Checkout team. That's the team that develops and researches behind the Amazon Dashcart line of products. And I'm very excited to be here today to present the second iteration of the Grocery Vision Dataset Challenge. The first iteration of this challenge was presented at the WACV 2024 workshop earlier this year in January. And as part of the second iteration, we've released 2 novel challenge tracks as part of the RetailVision workshop here today. First and foremost, I'd like to acknowledge all of the hard work that went behind the dataset challenges here. This is a team of applied scientists within Amazon focusing primarily on physical retail research, also our manager, Sean Ma, who's was here earlier today as well. And just a little bit of high level about what the Grocery Vision Challenge is meant to be about. First and foremost, it's a collection of publicly available data sets that are collected in realistic physical retail environments. They're hosted by AWS and free to download. Note that the licenses for these data sets are Creative Commons licenses, so they're mainly used, mainly aimed at academic research. But all you have to do is scan to our project website. Feel free to reach out to us, and we're happy to share the data sets that we've accumulated thus far with this project. The main objectives of Grocery Vision is to make public foundational challenges that the AI research community focusing in physical retail encounter. We're also looking to collaborate with the rest of the community with this endeavor. If you have future data sets or future conferences you'd like to participate, collaborate with us in, we'd be happy to hear about it. So the first novel dataset challenge track that we've introduced here in RetailVision is a video temporal action localization and spatial temporal action localization challenge, also known as TAO and STAO. With this double set of challenges, the aim is essentially to locate within a video stream the bounds of the activities of interest, the shopping activities of interest, including the label as well. And for the spatiotemporal component, it's also to identify the tubelet of interest within the video stream as well. These data were collected by the Amazon team in realistic grocery store environments, also by attaching an RGB camera to a standard US shopping cart, this particular challenge. The RGB camera overlooks the basket, and so you could see a number of different common shopping actions present with the shopping cart. The data set consists of nearly 300,000 frames of 271 videos, containing roughly 1,300 or 1,400 actions among 3 different classes. What we provide to the participants are, of course, the data and the labels, which are bounding boxes and consistent tracklet IDs of the actions within those video frames. Some unique challenges to bring up as compared to standard benchmark action recognition data sets. This is mainly a challenge focusing on products rather than human actions. If you look at kinetics or AVA or other benchmark data sets, they typically focus on the human actions that are present in the videos. For this challenge, we're focusing mainly on the products themselves. And this is sort of by design because when you're adding something into a shopping cart, you don't always have to have a human present. You could, actually throw items into the cart if you want to. Another thing to point out is that these are untrimmed videos, and so there is definitely an issue of data imbalance. And the classes are also fine-grained. A lot of the data set challenges that are out there today, the discriminative features typically come from the spatial information, meaning if you look at a single frame of somebody swinging a golf club, you can almost immediately tell what class that is, and you don't have to look any further. The temporal information is sort of extra. For here, the time domain is actually quite important. So for instance, adding an item into the basket, removing an item from the basket, they look identical if you flip the time dimension. And so for this particular data set, both space and time are quite important for the challenge. Lastly, temporary occlusions of items due to hands, body parts, other products are also present in the data set. There are sometimes multiple actions with similar or differing labels occurring at the same time. And lastly, the backgrounds are also very challenging, containing products that look very similar to the ones being manipulated in the videos. So here are just some examples from the training data set. The classes are fairly self-explanatory. Taking an item is placing an item into the cart basket. Returning an item is removing it from the cart basket. And rummaging are purposeful rearrangements of the contents of the basket without removing or adding something. So here's how we actually evaluate this first track. We actually have a holdout test data set consisting of 33,000 frames, also consisting around 150 actions of each category. And for the temporal action localization challenge, we use a frame mean average precision score, which averages over all temporal IOU values from 0.5 to 0.95 in steps of 0.05. And this is averaged over all classes as well. For the spatiotemporal action localization challenge, the only thing that's different is the IOU metric that we use to compute the overlap. And in this case, we're using what's called a tubelet IOU, which is a space-time overlap. The second challenge track is a multimodal product retrieval challenge. The goal of this challenge is essentially to retrieve the product identity from an open pool of candidate objects. And what we provide to the participants here is a number of different views of each product. In this particular data set, we have 400 unique barcoded products and roughly a couple of hundred or so views of each product, along with a textual description of each of those items, describing the visual features. And these descriptions were actually generated from a Lava Next model. So that we didn't actually scrape the internet, we actually generated it with the Lava Next model. And some unique challenges here include viewing all sides of product packaging, sometimes with not a lot of information present. A confusion set, which includes lookalike products. There's a whole category of items which look essentially identical to one another, if not for a very small amount of text. There's also partial occlusion by hand as well that complicates this data set challenge. For evaluation of the MPR data set, we have a holdout test data set of 1,100 frames. 460 unique products are used in the test data set. 400 are known products. So they're also contained in the training data set, but they're novel views. And we also include 60 novel products entirely to test the solution generalizability. During inference, what we do is we take the solution, we iterate over all of the frames, and the solution is expected to produce a ranked list of barcodes based upon the full gallery of text descriptions that are present. And we evaluate the model performance using the CMC, the cumulative matching characteristics metric. In particular, we use top 1, top 5, and top 30 accuracies. So without further ado, we'd like to announce that the winner of the Tao Style Challenge is the Tencent WeChat CV team. So please join me in congratulating the team. And we have a new leaderboard with their results present. Unfortunately, the team was not able to attend the CVPR conference this year. So once we dive into their challenge solution, we have a pre-recorded video. Any questions you guys may have, we'll pass along to the team. And for the MPR challenge winner, this is not a glitch. The same team actually won the second challenge as well, the Tencent WeChat CV team as well. So congratulations to that team once again. And we also have an MPR challenge runner-up that we'd like to announce as well. The team member is Sarthak Srivastava from the Amazon MENA tech team, and he should be here today to give his presentation at the end. Here is the challenge leaderboard for the second track. We had 3 submissions, and Amazon also provided a baseline solution, which was an MLP trained on clip features using a bag of tricks. And in this particular case, the baseline seems to be in roughly second place here. That's it. Thank you very much for your attention. And from this point forward, we're going to listen to a number of challenge winner presentations. We have 2 pre-recorded presentations, and then Sarthak is going to be giving his runner-up presentation following that. Thank you very much.
Steve,
yes.
One question. In order to get the first place, did they have to detail the solution? So tell us exactly what they did.
It wasn't a requirement, but they were offered a slot to speak at the workshop, and so that was their chance to basically detail the solution.
maybe next year that should be a requirement, right? Because then we make sure, okay.
They do provide details. It's more the pre-recorded video. We can take a look at what approach they were doing and what method they were using and why they achieved a higher score in the
Great.
leaderboard.
Then we can learn from that, make it public.
Yeah.
Help the
Yes.
community.
Absolutely. And one other thing I should mention is, even though, this workshop is nearly done, we always welcome additional submissions to these data set tracks. If you want to see if you can beat the, state-of-the-art method on these data set challenges, feel free to, and we're happy to take a look and evaluate your solution.
Yeah, another note is you can see here, we plan to organize another few workshops in the upcoming years. We hope that every half a year we can have a gathering. So the next one we hope to get to is the WEC 2025 in January next year, and then CVPR next year as well in similar time.
Thank you, Austin.
Okay, thank you very much. Appreciate it. You have to reshare my screen, right?
Can you try and reshare it?
It's not sharing it on Zoom.
Yeah, it's showing the previous.
Okay.
It is paused, so I need to reshare.
So, share.
Yeah, that's
Great.
Then you can minimize yourself by clicking on the little dot menu.
Hello, everyone. We are members of the WeChat CV, consisting of Jianhua Liu, Tianyi Wang, Kumai, Guangting Wang. We are delighted to be here today to share our solutions for the Grocery Vision Challenge. Our solution is a unified model for video temporal and spatial temporal action recognition. We start by analyzing data, 271 annotated training videos with a total of 298,167 frames. On average, each video consists of 1,100 frames, totaling 79,187 annotated frames across 4,165 actions. Typically, each video features between 10 and 25 actions, with the highest number of actions in a single video reaching up to 56. Overall, the videos exhibit a long frame duration and the number of actions per video varies considerably. The average number of annotations per action is 19. The distribution of action annotations in the right figure indicates that the majority of actions have annotations below 60, with the highest number of annotations per action being 240. 98.5% of the video features only one type of action. All annotated frames depict a single type of action. This suggests that a multi-class classification is adequate for the video temporal recognition task. Initially, the video frames are segmented into frame blocks, with each block comprising 16 continuous frames. Subsequently, a sequence of 8 blocks forms a training or inference block. During both training and inference phases, the video is partitioned into 8 frame blocks with a step size of 4. The temporal model structure is shown in the figure at the bottom right. The input consists of 128 frame pictures split into 8 blocks of 16 frames each. Initially, the images are passed through a pre-trained video MAE block with a resolution of 224 by 224 for feature extraction, resulting in embedding features of 64 by 14 by 14. Deconvolution is applied to restore the embedding to the original input length, while max pooling is used to capture frame representatives. Interaction across the 8 blocks is facilitated by a bidirectional long short-term memory layer, followed by an action classification layer. The spatial temporal model structure is more complex than the video temporal module. It involves generating action bounding boxes and establishing product bounding box relations across frames. We designed basic object detection blocks consisting of two components: an object proposal layer providing decoding cues and an interest-oriented layer for target-bounding box decoding. To capture box relations within or across frames, a relation classification layer was incorporated. We will further describe the model structure in detail in the subsequent sections. Like the example below, the object proposal layer is a basic classification layer used to determine the presence of an object for decoding. During training, all positions containing the target object or part of it are assigned as positive proposal targets, while those without the target object are designated as negative. We developed an interest-oriented object decoding layer inspired by CornerNet, with simplifications made to lower computational requirements. The process is outlined as follows. 1. Obtain the image feature map using the video backbone, video MAE. 2. Identify the interest points through the object proposal layer. 3. Extract the embedding related to each interest point as the proposal feature. 4. Resize the proposal feature to match the original feature map size and combine them, creating position decoding features with a fusion layer. 5. Perform max pooling separately along the vertical and horizontal axes to predict the start X, end X, start Y, end Y heat map regression. 6. Due to the low feature map resolution, each regression point will predict a 4-position heat map. Consequently, the input heat map regression feature has a length of 14, while the heat map target is 4 times longer to enhance location accuracy without depending on the resolution of the original feature map. The relation classification layer serves 2 main purposes. Firstly, it identifies relationships among various interest points within a single image, similar to non-maximum suppression used to eliminate redundant detections. Secondly, it identifies relationships among distinct interest points across images, enabling the association of objects across multiple images. This is a classification block that's designed to work as follows. The 2 proposal features from the same or different feature maps, where the interest point generated by the object proposal layer is subsliced out. These features are concatenated and fused using a fully connected layer, followed by a classification task to determine whether 2 interest points belong to the same object. This layer is crucial for removing redundant detection results within the same picture and linking the same object across sequential images. Here is the inference procedures. 1. The object proposal layer outputs the probability of action objects in all feature maps. 2. The interest-oriented object decoding layer decodes the object coordinates respectively. 3. The relation classification layer first removes redundant detections within the same picture. 4. The relation classification layer then associates the same object across frames. 5. When combined with the video temporal model, the action classes are associated with each object. We combine all part together and construct the final unified model for both video temporal and spatial temporal action recognition, as shown in the left. Both video temporal and spatial temporal action recognition utilize the same video feature backbone, VideoMe. The output feature map is used for both temporal classification and spatial object detection. This is the final leaderboard of our submitted model. Thank you for listening.
Great. Again, if you have any questions, we will gladly pass those along to the participant. Next up, we have the challenge winner for the NPR track, also the Tencent WeChat CB team.
Hello, everyone. I am honored to represent our team to share with you our winning solution for this challenge. Next, I will give my talk from the following parts. Our team name is WeChat CB, and our team members are Zhenyu Liu, Tianyi Wang, Kim Mei, and Guangting Wang. We are all from the Weixin group of Tencent. Our team mainly focus on AI research in CV, audio, and multimedia, and serve the multimedia business of WeChat. We have summarized several key points of our proposal. This challenge is a typical image-to-text retrieval task, where we need to recall the most matching text descriptions for a given query image. In terms of model selection, we have chosen 2 clip models with different visual architectures. Vision Transformer is now a widely used foundational architecture in the field of computer vision. With large-scale data pre-training, it exhibits excellent performance and is highly scalable. ConvNext is a pure ConvNet model constructed entirely from standard ConvNet modules. ConvNext is accurate, efficient, scalable, and very simple in design. We pre-trained these models on a large data set of captions generated from virtual image text pairs, and then fine-tuned them on the NPR competition data. Throughout this process, we employed several tricks to avoid overfitting and improve the loss function specifically for this task. The data consists of 2 parts: product images and product descriptions. The product descriptions appear to be generated using tools similar to ChatGPT with prompts. Each product has multiple images and descriptions, and they are not completely one-to-one correspondent. We use the pre-trained clip model to calculate the similarity between each product image and its corresponding 10 different descriptions, assessing the importance of different prompts. The prompt, "Describe the product in the image," is more relevant to the image and contains more visual information about the product. Additionally, we have analyzed the resolution of all images with an average resolution of 427 by 509. There are 409 distinct products, corresponding to 74,200 images, with an average of 181 different images per product. The overall data scale is quite small, and the diversity is limited. We use CLIP to implement image-to-text retrieval. CLIP is a very effective model architecture consisting of an image tower and a text tower. It can achieve cross-modal retrieval from images to text through supervised training with contrastive loss. Considering the diversity of the final model ensemble, we used 2 CLIP models with different backbones. One is the transformer-based VIT large, and the other is the CNN-based ConvNext large, both of which have excellent performance in image understanding. We adopted the implementation code and pre-trained parameters of these 2 models from Hugging Face. We pre-trained the open source models with product data, aiming to enhance the CLIP model's ability to recognize fine-grained products. We focused on using the recaption technique, employing open source MLLM models such as Llama and Internvel to generate descriptions for product data. Specifically, we used a fixed prompt, describe the product in the image, and individual image input them to the MLLM, treating the MLLM's output as the caption for this image. Through this approach, we utilized publicly available product images from the internet to generate a large data set of product description pairs similar to those in this challenge. We used this data set to train our CLIP model. During the fine-tuning process, we used an improved contrastive loss from Siglip called sigmoid loss. The sigmoid-based loss processes each image text pair independently, effectively turning the learning problem into a standard binary classification on the dataset of all pair combinations. Its pseudocode is shown on the right side of this page. Specifically, when the training batch size is large, there may be images of the same product from different perspectives within a batch. In such cases, these images of the same product should be considered as positive samples rather than negative samples. Therefore, We modified the original sigmoid loss to filter out such situations based on the product ID. Specifically, if the product IDs of an image text pair are the same, they are considered positive pairs, with their label equal to 1. If the product IDs are different, they are considered negative pairs, with their label equal to 0. It's worth mentioning that, since there are 10 different descriptions for each product in this competition, we cannot determine in advance which description matches the current image best. We used an extra trick. Before calculating the sigmoid loss, we first calculate the similarity scores between the current image and the 10 descriptions of each product. We then use the most similar description to form the image text pair and discard the other less similar descriptions. For positive pairs, this operation requires the model to find the most relevant description, making the training objective clearer. For negative pairs, this also allows the model to pay more attention to more difficult negative pairs, increasing the difficulty of training. Using the method described above, our model ultimately achieved the highest CMC score in the official evaluation. That's all we have shared. Thank you all for listening.
Very good. So we have one final presentation. You can ask a question, but the authors are.
No, I can take notes and then.
Oh, yes, yes.
Go to the organization.
Sure.
So as we saw in this talk that the description of the product was kind of automatized in a way. And is that intentional, or it was because you're introducing a bias and he's explaining that he had some troubles due to one product being 10 different descriptions. Is that an intentional thing, or was it like a unintended thing that happened?
It was intentional.
Okay.
We generated the textual descriptions because they can vary depending on the view, right?
Yeah.
So the visual features can change if you're looking at this side of the product or that side of the product.
Yeah.
And in order also to avoid scraping the internet and bumping into issues with, concerns with copyright, there's no concern about using the output of a lava model. And so that's the second reason why we did it. Yep.
Thanks.
Yeah, there's another reason is we try to, in the future, expand the data set. So the only way to expand the data set is without a lot of foundation model, generally like description, so to think about we can actually hire people to do this, but it's the same. Every person will have a different description of the product. Yeah. So likely we can combine that in the future with a human review.
And is the evaluation different for description rather than product identification? Because as from a customer perspective,
eventually we judge by whether the category is right or not.
Yeah.
Not on the actual description is right or not.
Yeah.
Did you share via Slack? Yeah. Okay. Stop sharing. Looks good. Yeah. That good? Yeah. Okay.
Hi all. So I'm here to present the solution for MPR challenge. My solution is based on blip architecture and use of a augmentation technique where I use Fourier transform. So the goal of MPR challenge is to retrieve the product identity given an image and pool of possible candidate products. The training input that we were provided included set of images and corresponding text descriptions. The data has been sourced from RetailVision dataset consisting of real-world grocery retail data collected from GoPro camera mounted on top of standard US shopping cart. And we were expected to devise method to retrieve accurately the identity of the product in image given a catalog of product description. So yeah, the dataset consists of 74K images mapped to their corresponding barcode via the file name. And there were in total uniquely 409 barcodes with a catalog entailing information such as description of the product, what is the tag description, shape, colors, and patterns. So the solution consists of two major parts. One is the blip architecture, and the second is Fourier transform. The blip architecture is used to compute image text match score. The blip model stands for Bootstrap Language Image Pre-training Model. It is a notable extension of the CLIP model that enhances its robustness and generalizability. And in contrast to CLIP, which learns using a static data set consisting of fixed image samples, blip is a more dynamic process. It generates new caption for the given image sample using its cap-filled model, which stands for captioning and filtering. So the first process in blip involves pre-training process, which is very similar to CLIP. It learns to associate a given pair of matching text and image to same embedding in some shared space. And it basically establishes a fundamental understanding of the image and text. Now there is a bootstrapping part where the captioning module generates different captions, and a filtering module filters out the irrelevant ones. So we can use now a new caption for our training process. So blip architecture, as I mentioned, it consists of two major parts. One is a mixture of multimodal encoder and decoder. The second is the cap fill part, which is captioning and filtering. And the solution that I'm discussing, I have been only been able to use the first part. The second part is for the future advancement. And the first part, the mixture of encoder and decoder, that consists of unimodal encoders, which separately encodes text and image in some shared space. And the image encoder that we use is a VIT base model for now. And the text encoder is a BERT model. Then the second pillar of blip model is image grounded text encoder. This injects visual information by placing a cross attention layer between the self attention layer and the feed forward neural network in each block of the text encoder transformer. So then there is image grounded text decoder, which is essentially same as image grounded text encoder, but it replaces the self-attention, bidirectional self-attention layer with the causal self-attention layer. So it is used for the generation of captions. And this is again something that we will try in our future iteration to improve upon the result to generate more and more captions. So a unique observation was that we have an image and we have description with several questions, and many of those questions might or might not be relevant to the image at hand. What do I mean by that? There might be an image taken from a top angle, while the description might have the description of product from different angles, and not all of them will be relevant to the picture at hand. So that's where the role of ITM role comes in. We will fuse information from image and text rather than trying to align them in certain space where it's not possible to align them because they have complementary information certain time, right? So while computing the ITM score, the self-attention layer from the text description is used to calculate the query matrix Q, while the key matrix key and the value matrix V comes from the VIT. That is, and these information are passed to the cross attention layer, which are then indeed passed on to the feed forward neural network to compute the final ITM score. The second part of the solution is about augmentation that we do. The key motivation of Fourier augmentation is to generate different variations of the input image, and by doing a style transfer. And for that, we use Fourier transform. Fourier transform is essentially breaking down an input image into a complex exponent of amplitude, frequency, and phase. The following formula is just Fourier transform for discrete Fourier transform for a given input image, for spatial domain to frequency domain. So again, within Fourier transform also, there are two major type of augmentation that we do. One is with respect to style transfer. We take an input image, we randomly sample some other image from the training data. We convert both into their Fourier transform into frequency domain. We swap the low frequency component of the input training data with that of the randomly sampled image selected here. And then we take the inverse Fourier transform of the input training data to get back the style transform image. And the second operation that we do is scaling of the low frequency component of the input data. So the low frequency component can be multiplied by a factor or divided by a factor greater than 1 to do something we call overstimulation and understimulation of the low frequency component. The following are the formulas for Fourier transform and inverse Fourier transform from spatial domain to frequency domain and vice versa respectively for a given 2D image. Here again, the formula describes the overstimulation, understimulation, and the style transfer process that we do. So in this architecture, you can see, for example, of style transfer as well as other augmentation that we are doing in our process. Here, this is a example of how the frequency domain and phase domain looks like after the Fourier transform, and how the image style is transformed with respect to that of the lower image here. So the idea here is to generate various representation of a given input image and penalize the model if it allocates different representation for different style of the image. So we want to ground our representation of text irrespective of what is the style of lightning condition and soft edges, which might be a concern in the grocery mounted US shopping cart mounted GoPro camera captured image. So again, for our evaluation, we have used the CMC score on holdout data of 1,000 samples. We compute the top 1, top 5, and top 30 accuracy for the proposed method. And for calculation of final score basis, which the sorting of different barcodes is done, we use a weighted ITM score and cosine similarity between image and text embeddings. And we use the holdout dataset to compute what should be those particular weights. Due to time constraint, we were only able to train the model for one epoch. And what we see in the data, our local evaluation and final evaluation were around 5% apart, and where our local evaluation was much higher compared to final evaluation, so kind of overfitting. Again, for k equal to 5, we had a difference of 6% around, and for k equal to 30, the difference was only 1.5%. So as of now, we have trained the model after the contest has ended. We have trained till 11 epoch, and it is still going on at the moment we speak. The local evaluation is at 78%. The evaluation for k equal to 5 is at 96%, while for k equal to 30, it's at 99.5%. And evaluation on holdout data still remains that Mohsin and Austin will help us with. For future work, as Tencent's team also discussed, we will use a more reliable description of the product images, and we will use that to further fine-tune our process. And I also plan on using BLIP2 architecture to leverage even larger LLMs to see how that helps us. And a third unique idea was like using NERF to generate, like use a combined few samples of image to generate a 3D representation and use that to identify what is the product. So that's it.
Great, let's thank your speaker. Questions?
Yeah, thank you for the talk. So before you applied the Fourier augmentation, did you notice that when you say purely in inference, when you applied that noise, the same noise from a different image onto a current image, say you have A and B, you've taken noise from B, you applied it to A, you passed clean A, and you passed the noisy A. Did you notice like a difference in the encoding when that got passed through before you even augmented and then trained? Was there a difference?
So in terms of performance difference on the downstream task, there was definitely an uplift on the 1,000 samples that we had held out. So was
Right,
around.
but I was asking like before even like passing through the training,
Mhm.
purely from an encoder perspective, was the noise creating that much of a difference in the information that was being learned?
To be honest, no. At before the contest, I didn't. But after contest, we have planned to do further EDA. But noise, you are referring to the difference between the computed embedding with respect to different variation. Then yeah, at that time we noticed that the values are completely different if we are doing the style transform with respect to different image. So if I do image transform of sample A with respect to B, and I compute its embedding, and I calculate it as E1, and I take just the blank image A and do its embedding with E2, there is significant difference.
Okay, that's what I'm.
Yeah.
Any additional questions?
So question again about the first transform augmentation. So what was the original idea, or why doesn't color jitter, for example, or other common augmentation techniques do the job?
Right. So other first of all, other augmentation we are referring to rotation and all those sizes, right? So
color jitter, changing saturation, brightness, hue.
Yeah, the motivation was to focus on the lightning condition and soft edges component, and there are other lot of augmentation techniques. So the key motivation was to generate different variants of a given input sample in a very cheap, computationally cheap manner as possible. There are other ways like cycle GAN and style GAN, but those are, you have to train those models, and that itself takes a lot of time. And this Fourier transform, we could just on the fly through an O of n squared time complexity compute a variant which is very dissimilar to the current original image. So that was the very motivation. And yeah.
You haven't compared it to color jitter or other common augmentation?
Not yet, but it has been explored in previous work with respect to just color changing and filter application and all those. And it has been established that Fourier transform based augmentation is more effective. We have a work citation here that accounts for that part. This one.
Okay, then maybe one more question. If you want to become invariant with these low frequencies, why not remove low frequencies?
Oh, if you remove the low frequency, the effect is quite drastic on the image. The content becomes either like if you setting it to 0, the low frequency component, it will become completely dark.
It no longer becomes a style transfer.
Yeah,
it's structural transfer.
It's structural transfer.
Yeah, depends on how or where you cut off, I guess.
Exactly. We take like 0.01% of the low frequency component. That has also been very carefully designed, because if you increase the low frequency component, you instead of just transferring the content, you start transferring the semantics of the image, which we don't want.
What was the effect of the style transform on similar items?
Similar item as in like same product or
similar product?
Style transformation, similar products.
That have a bad effect.
So the idea is to make the variation in performance agnostic of the lightning condition, right? So if it's the same product taken from a condition of low lightning, that will transfer on to the original sample. So that is also effective to some extent. You are kind of simulating a brightly lit image product in a setting of low illumination in that case, if it's the same product.
I mean, it's a different product.
Come again?
I mean, if you have two different products that are very similar one to another, so this transform might use details that distinguish between the two.
No. So that's why we select the very low frequency component of the image. The low frequency component only corresponds to soft edges and lightning condition. If you were to increase and go beyond the low frequency component, then we would be touching upon the semantics, and that is undesirable. We don't want to change the actual content of the image, just the style. And this is also like one of the limitations that we are not able to kind of simulate different views of the product. We are just touching upon whatever we can do in a very cheaply and on the fly manner.
Any additional questions?
So in the last slide, you have told me about nerves. Where does nerve enter all of this? Just to build a model, or?
This is just a discussion on the future work that we want to simulate the 3D product in the using nerve model, and then use that to create model that identify the product identity.
Okay, just the visualization.
Yeah, exactly. So that you know, through cameras we can only get product image from certain angles only. But what if we are able to visualize it 3D and then generate its identity? That ought to be more reliable and better performing.
Any last questions?
During the data collection, was it fresh products also a part of it? Like we see a lot of packaged products.
Fresh
here.
produce, right? That's your question?
Yeah, like bananas.
Yeah. I believe that's a good question. They're barcoded items, so the answer is no. They're all center aisle items. Nothing with a PLU sticker. Yeah. But that would be a great next step for the data challenge.
But that is the plan to increase this data set, right?
Yes, from here on out, we do plan to expand upon the existing challenge tracks, and we would like to also add new challenge tracks as well. Yeah. Great, thank you very much, sir. Thank you.
Thanks all.
Okay, so this is all for today. Thank you everyone for joining. Thank you, Rost and Sean and all the guys for the great work with the challenge. I know it's a lot of work. And if you have any questions, you'd like to talk, you'd like maybe see about presenting next year, please talk to us. Thank you.
Okay, so thank you. And I'm sorry for this long preparation, technical one. So I'm Yossi Keller. I'm a professor at the Faculty of Engineering in Bar-Ilan University. I'm also a principal applied scientist in Prime Video with Amazon back in Tel Aviv. And today I'll discuss my journey. It's a short journey into foundation models and how I started to understand what they're all about. Because yesterday I went to this foundation model workshop and they show wonderful works, but then they were talking about training a foundation model on 100A100 they are called, or something like that. And typically we only have like 2 GPUs at my lab, like each server has 2 3090s. We don't have 100, we'll never have ones. And also working in Amazon, we typically do not train 100 GPUs. Most of you typically don't do it anymore also. So I would like to show a different perspective of what foundation models are and how we can use them at your particular applications, because typically we don't need these huge models, right? It's also very expensive to use. So I'll skip some of the parts here because it's also meant to other talks I give about. I also provide some background about transformers. So it's less interesting here, I think, because we have this kind of CVPR audience. So if you are unfamiliar with attention transformers, please learn it. That's like the foundation of deep learning over the last few years, and in some sense, it's just becoming more and more dominant everywhere. If you go over the talks in this CVPR, everything is just transformers. If you look at the lower level of what people are doing, it's just that. So I'll skip this also. And actually, what I wanted to show here, this is an old paper. Yeah, we should get rid of this part. Yeah, no, this thing. How do we get rid of this? Like that?
Yeah, just drag it down all the way down.
Oh,
There you go.
it disappeared. Also, I don't want to see myself. I'm used to that.
Yeah, can click on this.
Yeah, good. So I'll just say that the notion of attention is old. This all goes back to 2014, 13. We had all of these papers about bilinear pooling, which is actually the basic notion of attention. So you have the image going through two CNNs, and then you compute the cross product between all elements in the activation maps. And when you see nowadays a lot of these efficient transformers, they use the same tricks, like low-rank approximations and other kind of things. It all goes back to that. And the great thing about 2017, where all you need is attention came out, is the fact that they did it very technically efficient and very it works very well. So the way we got into that, and this relates to the paper that we're going to show tomorrow here in CVPR, is that that was our path into that, is that we are interested in problems where you had interactions between two images. Typical problem might be stereo, might be rotation estimation, localization, anything where two images are going to interact, implying that they're going to be used as input. And the common structure that was used for that was the 4D correlation volumes, which are just an attention surface, right? So they're called 4D because you instead of vectorizing the activation maps, they just treated them as two-dimensional objects. They're actually three-dimensional because you have also the features, and then you compute the interaction between them. So you get a 4D tensor, right? Because you have 2D and 2D, and each point interacts with each other point. So overall, you get this 4D surface. And this is like Raft, which was the best paper 2020. And I got interested with this paper because I had Hadar Averbuch visit us in our university. So this is a paper about rotation estimation. And it's really nice to, it's initially, it looks like witchcraft, like Gerard mentioned before, because they're able to estimate rotations with images that are not even overlapping, which is amazing, right? Isn't it? And all of them, when they interface two images together to get some inference out of that, they use this 4D CV structure. Again, it is just the attention between all points together. So I got interested into that, and I told Hadar, I think that we can do it better with a transformer. Why? Because it's the same essence, but you have a lot of this machinery inside, right? So if you look at it through a transformer decoder or encoder, you have all of the skip attentions, you have all of the normalization, all of this kind of structure is already built in. You get it for free. Also, you can then stack it, right? Because we don't use a single attention layer, we have multiple. So that was the point where we started. And yeah, so just to give you a hint, why is that interesting, and why do we need this kind of interaction between all parts of the image? Because so these are images with a very small overlap. I think that this thing, this is this, okay? So the overlap is very small, but still we are able to estimate the rotation. And the trick is very simple. So initially it seems like a kind of magic, but the idea is that if you have corresponding parallel lines in both images, then parallel lines, they define the rotation angle very easily. By the way, if they are parallel and they do not coexist, they do not overlap, it doesn't matter, right? So if you look at this room and you look, say, at the ceiling, you have these parallel lines on this ceiling. If you want to estimate the rotation angle, one of them, the parallel lines do not even need to overlap. Just take two parallel lines that are known to be parallel, and you can compute the rotation angle, right? They just have to be parallel, that's it. And they do not have to overlap. So this is a typical example where we need this interaction between all elements in one image and all elements in the other image. Why? Because it's a global property. The rotation angle is a global property. Okay? That's why. A counterexample, if you work in face recognition, or like Gerard showed you, the palm, attention doesn't make sense because it's aligned. There is no need, if you work in face recognition, for my left eye to interact with my chin. There is no information there typically. You might need to define an attention, a horizontal attention. So left eye interacts with right eye. Why? Because our face is typically symmetric, right? So understanding the nature of attention is crucial for many applications. Therefore, if you look at face recognition papers, they don't use attention because it doesn't make sense, right? So it makes sense to define this, and you can do it in PyTorch by defining one of the masks, the 2D mask, which allows you to define exactly the locations for which the attention will be computed, right? So it makes sense to have horizontal attention in images. Same if you're doing stereo. So if you have aligned images in your stereo, and you have people or lines that are horizontal, and you want to work with that, typically if you have a card, and the card goes on a floor, and the floor is flat, then when you have two cameras, then the stereo is here, right? It will not be rotated or anything like that. Then it makes sense to use this kind of attention. So this is the paper we did that you will be able to see tomorrow. Out of all of this, only this part is the cross attention, which basically what goes on here, we have two images, we encode them using a CNN, and then we allow them to interact one with the other. Now, nowadays, I will not do it like that. I will not use a transformer encoder and play around. What you can see here is that in order to get the images to interact one with the other, we have to define the mask. Okay, the mask that defines which parts are going to interact with each other. So I just want one image to interact with the other. Now, the right way of doing that, and everyone is doing it right nowadays, it's called decoder-only architecture. You'll see it everywhere. It's called foundation models. So it's exactly the same, just a better way than we did. Okay, so that was our initial idea. And then we have some additional parts that I will discuss later, which are more like enhancements. And I started seeing them in other papers too. Some of them preceding us, some of them succeeding us. So all of this notion is like the general framework that you will see nowadays in most papers. For instance, I just want to show you, I was at the AC meeting, and at the AC meeting, they were talking about this great paper called Duster. So if you're not familiar with Duster, please get accustomed to it. It's about 3D reconstruction and calibration of images. So if you look at Duster and you look at the architecture, it's the same architecture that we are using because everyone is using that, okay? So this decoder-only architecture, I just saw it yesterday and said, okay, I know this architecture. So you have two images. This encoder just enhance the features, okay? This is self-attention, right? So typically you will have an encoder like a CNN or a VIT or an MVIT or whatever. Then you pass it through a transformer encoder just to enhance the representation. For me, it's just transparent, but it typically improves by a few percent. And here you have the interaction, right? So this is a transformer decoder that has the interaction. Everything to this going from here forth is just task specific. So they reconstruct the 3D of the two images and then the alignment. It's not really important, but what you should get from here, and this is very good. It's like the successor of Colmap, if you're familiar with 3D reconstruction and calibration, is that you have the interaction here through a transformer decoder, and before that, you have an encoder which typically includes any backbone you want, and then some kind of transformer encoder with self-attention. And there are other tricks also that I might show you later, time permits. Okay, so I just saw it yesterday and I saw that everyone is doing the same thing. There are many papers like that. And specifically, yeah, I have to drag it down, right? So, yeah, it doesn't disappear this time. It's consistent. Yeah, okay. I'll go here. Oh, never mind. So, so I got part of, I got this task to do back at Amazon, which was to do a few shot detection. And it was a simple one that can be done with a simple correlator. So my boss told me, use the correlator. And I said, no, it's too easy. I mean, I want to learn a little bit about zero shot, K shot. Zero shot is not typically interesting, but K shot makes a lot of sense. Why? When you have any application, you can ask someone or just ask yourself to annotate like 50, 60, 100 images. That's easy, right? And then you really want to create the first model and then start iterating, right? And you can look at some segment anything model, how they did that on a larger scale. So I looked at that paper and I really liked this paper because it's simple to understand and it works well. It sorted some of the data sets. So it's a very similar architecture. So let me show you what's going on here. You have an interaction. For a second, forget about the multiple inputs. Okay, let's say we have just this tutorial. So we have a target image. We have one template we want to find. So what's the architecture? The architecture is very similar to what we did, and it led us to understand that we are able to do a lot of tasks using this kind of architecture, and typically everyone is using that. So that's like the take-home message. So what's going on here? You have a CNN to encode. That's easy. This part is just an encoder, just enhances the representation. Nothing interesting there. I mean, it improves the result, but nothing fundamental. And then you get the decoder, which creates the interaction between the two images, right? So one image that we are getting is the target image, and then we get the template. So if you think about it, what's going on here actually, and I skipped the slides about the inner workings of a decoder and attention, just inner products, right? It's a very simple correlator. That's what's going on here. The attention map is just the inner product between the representation of the query and the embedding of the target. So what we actually did, if you think about it in terms of correlators, going back 20 years ago, we switched from having a correlator on the initial representation, say RGB pixels or HOG or SIFT or DAISY or all of that great features going back 10 years ago, we switched to having the correlation down here in the decoder. And this is a multi-head correlation because we have multi-head, it is stacked, but that's what's going on here. And then you get the result, and this is very nice and gets you up to very close to SOCA. Yeah, so I started playing with this architecture because I understood it. And then I saw the grounding Dino one, and then it becomes even nicer because it tells us that if before, in order to create an interaction, I put in two images through the same CNN, now if I use a multimodal model, backbone, say clip, blip, or even one that has additional things, I can now interact text and image, right? Because they are embedded in the same space. That's the thing about multi-modal embedding. So you can create interaction between two images, between image and text. And later I'll show you that you can add whatever prompts you. So this now comes in the world that everyone is using now, which is called prompts. So this is just a prompt, right? The only thing that is important is to have the prompt and the target to be at the same embedding space. So in multimodal embedding, it's given to you. So just to show you what's going on here, the feature enhancer is a decoder encoder I've showed you before. They do it a little differently, but than we do, but very similar. And here we have cross-modality decoder. So again, if you go, especially in this particular conference over many papers, they use the same architecture. And in my understanding, because it works, okay? So if you are going to build a model, think about it. I think that all foundation models are built like that, decoder-only architecture, right? So you have like initial enhancement of the features, and you have the cross-modality decoder, which is the decoder-only architecture, and we can later enhance the results. That's another trick that we had to do to get accepted to CVPR, because the core idea was not enough. We had to do some other stuff. Just as best practice paper for embedding prompts, I suggest you read Segment Anything. It's a great paper, a lot of interesting things, like two fundamental, I think, issues. The first one is how they created a data set of 1 giga of images automatically. So I will not go into details because that's not the issue of this talk. The other thing, technically, and out of like 20 pages, you just have to read like half a page. I mean, for me, that was really interesting. They explain exactly how to embed all of these prompts. So you can take the model you had before, you can add prompts as many as you want, and they tell you how to do it. It's not difficult. So the text is text, we already saw that. Now, for the other ones, like a box, a point, and so forth, they just learn the embedding or use positioning or fixed position embedding. Very easy. So the intuition is like that. If you want to add a prompt that is, I would say, large scale, like text, you probably need a pre-trained model. But if you're going to add whatever prompt you have in your application, it might be, say the class of an object, or if you're in the medical domain, is the subject in the image a male, a female, smoking, not smoking, young, old? You can just learn an embedding layer, right? Because that's easy. That's not a lot of parameters to learn. So you can really play around with all of this. And this leads us to the second point, and that's the important one, is that all of these prompts are embedded in a latent space, and they are merged together, right? Here. So there is a correlation between prompts. So you might write, I want to see, and there is a nice example in one of the papers. So there are like 2 dogs, and the prompt is, I want to see the left dog. So it is equivalent to saying, show me the dog, and clicking on the left, right? So in the latent space of the prompts, you can learn one prompt and then add another one. And it's like transfer learning. You already semantically have learned the new prompt because it is correlated semantically with the previous ones you had. Like if you train it by clicking, it will support the text prompt, show me the left dog. Okay, because left will be semantically embedded rather fast and will be applied to the image, because you've already embedded the notion of left and right, say just by clicking, or say just by using an object detector that splits the image into left and right.
Okay.
So
like 5 to 10 minutes?
Yeah, even less, yeah. So you see? Yeah, conclusions. Yeah. So there are many conclusions. So I have 10 minutes. So what I've shown you are the building blocks of foundational models. Again, for me, a foundation model does not have to be a huge model, because we don't do, both in my research group and in Amazon, we don't do foundation models. That's not our job. We solve problems, right? And when we solve problems, we might use a foundation model, but doesn't make sense to us, and we don't need to use like 100 GPUs. We typically use 1, 2, 3. That's what we need. So this kind of image to X interactions, image to prompt actually, that's actually the right way of saying that. Might be an image and text and clicks and metadata about particular object are an important task. And I would say that most of the papers here in this conference you'll see are around this kind of interaction. And the transformers decoder-only architecture is like the backbone of that. And we can use it, once you understand that, whatever prompt you have in your application, if you have music, just embed it. If you have video, embed it. So once you understand this general architecture, it becomes accessible to all of these kind of applications and metadata. It's still a lot of work. Yes, we have to train the models. We have to do a lot of work. We have to write all of the loaders that are typically takes time, and to import the data. I mean, those of us who write code, then it's work, right? Bringing the data, organize it. there is something very specific about text prompts. Because of their semantic value, they're very general purpose. So like I said before, the dog on the left. So a lot of things, I mean, as humans, we communicate via text, right? Writing, speaking, and so forth. So this is very valuable. And luckily for us, there are great language models. There are great multimodal models that we can use. We can do pre-processing to the queries using NLP, and only then inject them into this kind of model. We can do a bunch of stuff. We can aggregate them. We can agglomerate them, say, using RAG, and then improve the text. So we can easily add new models because at the end of the day, many of the prompts coincide or correlate one with the other, right? So sometimes, like Gerald said, at Amazon, we are CX oriented, so customer experience. The customer wants might want a particular prompt because that's the way he is used to. So you can train on one prompt, which is easier for us technically, and then switch to the other one easily. Okay? Sometimes it's easy for us to create certain prompts, but the user wants a different prompt. Why? Because he's used to that. I work for Prime Video, so people have been watching TV for 70 years. It's very, we have to be always very careful not to change the user habits, viewing habits, right? Because it's a very old industry. People have viewing habits. So the same here. Now, in practice, typically we would like to use the large foundation models, but then distill them into smaller models. If you are going to use a model 1 million times a day, you cannot use these huge foundation models. They're too expensive. Running Llama, whatever, 7B or 50B or whatever, all the time, I mean, it's not part of Amazon, but of Bedrock, but these huge modules are too expensive and too slow. So when we have task-specific applications, we'll have to do some kind of distillation. Another thing that will happen is that the more specific the task is, the better accuracy we'll get. There will be no hallucination. If you have a general model and you ask him how to make a pizza, he will write garbage, right? You probably remember the example. But if you train your model on Pizza Hut or whatever specific data, there will be no hallucination. So we have to become specific. Okay? And this is the way, I'm finishing here, and this is the way that I view our work. I mean, not only academically, but also in practice. Take home message, build your own foundation model, it's fun. I've been playing with this zero-shot detector. It's nice, it's fun, not a lot of training and small-scale model. I'm close to sort of. Hopefully next year, if it gets acceptable, show it here. And one last sentence that at the end of the day, to finalize the entire story about the zero detection, like Gerald said, we have this attribute in Amazon, which is called invent and simplified. So I didn't use any of that. I just used the regular face correlator, going back 20 years, and it works very well. So this is nice, but sometimes we have to do very simple things, and it's enough. Okay? So thank you very much. And if you have any questions, I'll be happy to.
Time for a question?
No questions. Everything is clear. Yeah. Well, thank you very much.
Yeah. Thank you. This is connected. Okay, so this should be okay. So we can share a screen and we make sure that Zoom does not bother the interface. Okay, so let's minimize this. And yeah, I think it should be okay if you enlarge. Okay.
Yeah. Thank you everyone for attending our workshop. And I'm Sharmin Rahman. I'm a research scientist at Amazon Dashcart team. I'm very excited to be here today and present our work on larger scale mapping in physical retail space. So what is mapping? So in general, mapping means that you want to know what is around you, your surrounding environments, and how they look like. So what does it mean in physical retail space? So in physical retail space, we want to know like where are the aisles, where are the shelves, and in short, what is the layout of the physical environment of the physical store. So, and we want to do it without any prior knowledge of the environment. Like we don't know, we didn't go to the store before, we don't have any information about the store. And we also want to do it in a very low cost way. Like we don't want to use expensive sensors like LiDARs or multiple LiDARs to create dense 3D point cloud, and which also incur very large computational cost. We don't want to do that. But at the same time, we want to have very high accuracy and robustness, because physical retail space, this could get very big, like usual physical retail space could range from 25K square feet to even 70 to 80K square feet. So we want to do mapping in a very reliable way and robust way. And at the same time, it has to be accurate. So we have the detailed layout of the physical space. And so for doing this mapping process and for low cost sensor, we chose camera, an RGB camera, and IMU. So this is the minimal set of sensors that we want to use. And if you want to create a dense layout and a dense 3D structure, you can have an optional depth camera. So all these sensors, like combinedly, they cost less than $500. So here you can see a top-down view, like which has been created just using a camera, RGB camera and IMU. And here you can see all the shelves and aisles. It's a very big store. It's like 40K square feet. And on the right, you can see there is also the trajectory, which has been the trajectory that has been generated to create this map. So why we need mapping? So the largest application for mapping is to enable localization. So where you are, if you are in the store, you want to know where you are and what do you earn from that. From that, like let's say you are searching for a product, like here I'm searching for this product. I can know like where are those like a possible set of products, and then we can navigate to it. So it basically enables GPS-like navigation, but for indoor environment. And there are many more applications that you can create, like if you have the localization information, like for example, like what are the products recommended for you, or it could be even personalized based on your previous purchase story. So what are the challenges? Why this is a difficult problem? Because you might think that this is indoor space, so we don't have like it's not as challenging as outdoor. The scene doesn't change much, like it's like not day versus night kind of lighting light change. There is also like no severe weather condition that you need to face. There is no snow, no raining, nothing. So why it is difficult? It's still difficult because like there could be like problems like we are doing vision based, right? So when you don't see, when you don't have good visuals, it is problematic. Like it is problematic to understand what is around you. So here I have some video like where it was collected. Like this is real data for our mapping. So in these videos you can see that there are severe motion blur. there are also structures where most of the time you really don't see anything. You see plain wall, all it's kind of near textureless area. So in this kind of environment, you cannot actually track like where you are based on your visual features. So in these are kind of like failure scenarios which we need to overcome. So here I mentioned just two of them, but there are more challenges. Like for example, like the data collection process could, for this large space, could become very long. Like it could take even more than 1 hour or 2 hours. So you can have accidental camera blockage. Like your hand could fall there, and you could the camera is blocked for 5 minutes. What do you do in this sort of cases? There could be very bright sunlight, and it could block the camera. It could blind the lenses. So what do you do in these cases? So in this talk, I'll delve a little bit more into the details, like how we take into these challenges and solve them. But before going into depth, like let's focus on some of the terminologies that we're gonna use here. So the first one is like VO or visual odometry, and another one is VSLAM or visual simultaneous localization and mapping. So VO is like if you have a sequence of images, like ordered images, like for example, what you have in a video, then VO, the task of VO is to determine the camera, the position of the camera, actually the pose of the camera, which combines both position and orientation of the camera, and from this sequence of images. So underneath it is like you have sequence of images, you detect features and descriptors, you match with them, and then like you triangulate them, some of the struct feature into the 3D, then you project them back and you optimize some function based on this to get your camera pose. So that is visual odometry. And all these things happen, like visual odometry happens most of the time in real time. So that means you cannot actually, like, let's say you have a 20 minutes video, you don't keep track from the very beginning to the end. You go in a window. So that's how you keep it real time. And there is the second one is visual simultaneous localization or mapping, VSLAM. So in that, what you do, like in that, what you do, like you have an optimized path, a globally optimized path, in contrast to the visual odometry. So visual odometry only cares about the local consistency, but in contrast, in visual SLAM, you have a globally optimized path. So it still goes in a sliding window way, but what it does, when you revisit a place, it uses this constraint to globally optimize all its previous poses. So, and the revisiting a place, usually the term is loop detection. So when you detect a loop, you get some constraints from your previous observation to your current observation, and then you use this to have some optimization constraint to use them as a to use them as a optimization criteria and reduce the drift of all the closes that you have observed so far. So here I have some video like where you can see the feature tracking happening, and that there are different colors. Green means there is high confidence in tracking, and here you can see the trajectory is generated, and also there is a sparse map from the sparse point cloud. And this has been done using just RGB camera and IMU. And you will also see like here, this is a SLAM process. So that means whenever a place is revisited, like for example, it just happened now, like you can see the trajectory has been shifted. So this criteria of the loop detection makes all the poses that you have observed so far optimized. The next time is like SFM or a structure from motion versus VSLAM. So VSLAM or visual odometry, both of them are real time, and that's why you go in a sliding window way. And that also has problem. That means like, as you are going in a sliding window way and, you are like throwing out rest of your pose, which are not in the sliding window, you lose information. So it's not globally optimized. So In contrast, in a structure from motion, both your pose and the point cloud that you have, all of them are globally optimized. So, and that also comes with cost because, like it is globally optimizing all your poses and the 3D structure. So usually this method is offline. And, like some popular method for doing SFM is like, for example, FullMap. But it has a very high computational cost. Like, for a several minutes video, it could take several hours, even if you have high, even if you run it on GPU. So here I talked about, like, we want to use visual inertial SLAM. So that means, we have RGB camera, and we also want to use another sensor, IMU, which has accelerometer and gyroscope. So the reason why we chose IMU is that it is, first of all, it is cheap. It is, you can get it everywhere. Even your cell phone has an IMU. So that's one reason. But the other reasons are like monocular camera just by itself, it cannot produce correct scale. So by monocular camera itself, you cannot get the exact like a scale of any environment. So you need the need of another sensor. It could be another camera like a studio camera. It could be IMU. So here we chose IMU because it's very cheap and you can get it everywhere. And more reasons are, it's though it's the IMU that we use, low cost, it can give you some post prior based on its gyroscope and accelerometer data. So this post prior can be later optimized or more corrected using your vision constraint. And this post prior also helps you to run some of the algorithm for visual odometry much faster. Like, for example, for visual odometry, to track features from one image to another, like you need to do some sort of like matching. So those matching could be much faster. And also for, like, let's say you are optimizing your, optimizing your error function based to determine your camera pose. In that case, you need to use like very popular, PNP ransack. So those PNP ransack, instead of 5 points, you can do them just using 2 points. So I have some references there. You can look through it, like how we can use them to not only, make our algorithm more robust, but also faster. And there are more advantages, like, like from IMU, you can get your motion prior, and that gyroscope actually gives pretty good motion estimation, rotation estimation. So in your next image, you can search it more efficiently. Like, you don't need to search through all the places to match image to match image frames, features from each frame to another. So the question, I think, like one of the most popular question is like, there are many SLAM packages, open source SLAM packages. So why do we need like other SLAM packages, another SLAM package where they show to be like having very good accuracy, like they have millimeter to centimeter accuracy. So why do we need another SLAM package? So here I compared some performance of a very popular SLAM package like OutSLAM 3, and another is OpenPins. So this data set, this is a larger scale grocery data set. The duration is around 1 hour, and the size of this story is around 25 square feet. But as you can see, OutSLAM, like it is started, but within several minutes, like around 10 minutes, it cannot keep track at all. Because because of this high volume of data and all the processing, the high processing phase that's running for visual odometry, is not able to generate or continue further. In OpenPins, it's comparatively performs better, but you can see that there is high drift. The reason is OpenPins doesn't have any global optimization module, which is postgraph or loop detection module. So that's why, like at the beginning, like over time, as these all of them are SLAM method, that means it follows sliding window optimization, it starts drifting. So for large scale, we must need some sort of global optimization that keeps us on track. So that keeps us and like correct our pose periodically. So instead here, if you see our method, you can see like in gray dashed method, we call it EcoSlam. You can see that it has generated the trajectory and it tracked for the full time without any problem and has generated good trajectory. And this is the overlap trajectory of all this. So this is the workflow. I'm not gonna dive much into it because I'll talk a little bit of some of them a little bit later in my slides. But here, one thing that I want to focus on is like what is different in our method from rest of the other methods. So what do we do? Like failure in Visual Slam, it's sometimes it's obvious, you cannot avoid it. Like if someone accidentally block your camera, you don't say anything. What do? You don't have anything to do because your method is based on vision. So what we do is like we detect failure, and then like when we detect it, we try to like recover gracefully. So failure would happen, like it's sometimes unavoidable, but we detect failure and we try to avoid, or we discard those failure moments and then reset accordingly. So here are more about the like how Visual Slam happens. So this is not very specific to our method. This is a very general method. Like if you have multiple sensor, like how do you fuse them? Usually you fuse them in a tightly coupled way. So you jointly optimize all your sensor error terms from all of your sensors. So as in this case, we have RGB camera and IMU. So we have 2 error terms and we jointly optimize it to in a sliding window manner to get our camera pose. So this talks more about the reprojection error. Again, this is not something different. It's very common. It's like, reprojection error is simply like where you observe a feature and then like if you have a point and you are tracking them, the corresponding 3D point, if you project it back into the camera, what is the difference between them? And here is about the IMU. So IMU gives you gyroscope measurement or accelerometer measurement. And the way it is integrated is actually like we call it IMU pre-integration. That means in between 2 camera frames, you take all the IMU measurements and you pre-integrate them to get a pose prior. So you get a prior for position and you also get a prior for orientation. And then you use this pose prior for your reprojection error term to correct it. So it's like prior helps you to get better estimation and better correction from your camera observation. So, and then like in sliding window, what happens when you move to the next window, like to the next frames and your pose are marginalized? So when you throw out pose or throw out information, that means you are losing information. So losing information is not good. So what do you do? So when you lose this information, what do? We get a prior from this marginalized post, which we use again for the next optimization as a prior. So basically, from the we use the information for our marginalized information. That way we keep it more accurate. And here comes the global optimization part, loop detection and relocalization. So that means like if you previously visited a place, then can you generate some constant based on that? So you have previously visited some place, that means you have some common 3D points and you have the matched feature from your previous frame, like your first visit to your current visit. So based on that, can you generate a constant? So here we can generate a constant, which is basically, so we can generate constant, so which is basically the difference between poses, and the pose would come from this common observation that we have between these 2 frames. And then the next module, which is like failure detection and recovery. So failure detection is like failure would happen. So how could we detect it? So there are very common metrics that we could track to identify failures. Like for example, if you are in your current frame, how many features do you see, and from how many places it has been seen. So we call it co-visibility. So if you like, if you are in a place where you don't see any previous feature, like I'll give the example of the camera blockage scenario. So your camera doesn't see anything. That means your image is completely, let's say, black. So you don't have any co-visibility. So you're gonna see the co-visibility metric to be 0. So that's one way. But is this enough? No, we need to have more metric to reliably detect there is a failure. So other metrics are, for example, how many 3D features you can successfully track and what are the quality of them. Are they good? They have good confidence based on the covariance metrics, like how confident you are. Then another good metric is like ratio of detected features, newly detected features. That means, like whenever you have failure, the module, our estimator will try to detect more features. So a lot of new features, like in case if you have failures. So in that case, you can also identify it's not tracking, so it's trying to detect new feature. And the last metric is like it's the velocity. Like it's based on observation. Like for example, if you have a drone, it should have a maximum allowable velocity, right? Like it cannot go like let's say speed of a plane, right? So these are the common metrics, but it is like very common metrics, but it is still helpful to detect failure. So other things to support, like for long-term mapping and larger scale mapping is multi-session mapping, we say. So which is like, let's say if your store changed, some of the aisles, some of the shelves has been removed and there are new shelves and new aisles. So what do you do? So you can create, like you can collect data. You don't need to recollect any data, just collect data from the changed area and you can merge them. So similarly, like let's say you are collecting data and you are too tired, you don't want to continue the data collection. You collect it for half an hour, then someone else come and can collect data for another half an hour, and you can merge all these mapping information into one, and it still will be able to generate the full map. So I'll include some more details, which basically says like, even if we are doing like visual SLAM, we don't do expensive computation like a structure from motion. Like then, like what about, we get optimized posts, but what about the sparse point cloud? They are not optimized. How do you do? So in this case, we actually update the point cloud based on our optimized post. So which might not be as accurate as like a core map like method, but it still is consistent enough. So here there are some more math. I'll not go into deep. It basically says the post graph optimization, how you can formulate the cost function based on the constraint of revisiting a place. And lastly, I would like to show a demo of our low cost sensor based dense mapping. So this is a 40K square feet store. And for dense mapping, there is nothing fancy done. So it's still like a visual inertial SLAM, but the depth images from the dense depth images from the depth camera is just has been registered against the like visual inertial SLAM, and this point cloud is generated like this. So nothing fancy, it's just the post registration. So here you can see like, like all this processing, even if we do the mapping, our mapping process is offline. It's actually like when we run it in the background, like it's actually real time. And this data collection was like around, I think 70 minutes. And the size of the store is like 40K square feet. And the computation, it also doesn't require very high computational resources. Like for example, this was running in a 8-core CPU with a 32 weeks memory. So it's still real time. It's not that computation hungry. So with that, I'd like to conclude my talk, and I'd be happy to take any questions.
Hi, great. I thought that you already answered that, but I will ask again because I'm not sure. Typically, I would think that when you go into a store to put in the cards, you have like a few days to prepare things. So why not use a global method? Why go to SLAM? Because what I thought about was I would just take out all of the information, and if it takes 4 hours to compute, no one cares because it takes a few days, maybe a few weeks to prepare the store to get the new cards. So why do you use SLAM instead of the global method?
Yeah, this is a very interesting question, and I'm glad that you asked. So we actually tried. So one very popular method is pole map. So what we did, like we tried to see pole map for our ground truth. So what happened, like pole map, it is not even able to keep track. Like it's very computational heavy, and it is not even to keep track even for 5-6 minutes. So and we did it in a very high computational GPU, like there was several like 10 V 100 GPU. But what like first of all is like is not even able to do like process more segment. But another thing is that like when there are motions which are not very smooth, like abrupt motion, like for example, you were collecting data, you were running in this very high speed, or like rotating harshly, it is not able to keep track. So we we have a paper we submitted. So for that, we were trying to get a pole map working, but even like, a lot of manual pre-processing, having good segment and trying to join them, because pole map is also able to join multiple models together. It was like what we got best is like around 10 minutes of data to be
at most to be able to.
Yeah.
What kind of precision do you see, like distance-wise, that you're getting in meters?
Yep. So we don't have any ground truth. So the way we have done some sort of accuracy measurement, it was like taking the distance between 2 points. So for example, we would measure the length of the whole shelf and manually versus from our dense 3D point cloud and see how much is the difference. So we have seen it differs like couple of centimeters, 2-3 centimeters or like that. So which you calculate in terms of percentage is like much like 0.2 or 3% of distance error. Yeah.
Did you have any 2D relaxation with regard to your task?
Sorry, 2D?
2D relaxations with regard to your task. Your task is to find your location, right, in 2D space.
Yes. So your question is how do I use this information for localization?
I mean, you don't really need the 3D information, right?
Yeah, we don't really need 3D information, but we need a top-down view of the store. But so if we need a top-down view of the store, you actually like we need to detect the layout, right? So for example, like not all the things will be at the same height, right? So you need to have some idea of how the height changes, like how are the shelves. So if you just consider in a plane, like for example, you are going like the area is mostly plain, but what if you have a stairs? Like sometimes you have a stairs and you need to go, and like all the shelves sometimes are not in the same height. Like the mid shelves, they have a like very high height. On the other hand, when you go to bakery section or produce section, they are much lower. So same height constraint is actually I would say it's not a good constraint to put. Yeah, go ahead.
I think the two major problems that you called out was one was the low features, which kind of gets covered by like the multi-session or like the poor tracking in the value. The other was motion blur. How are you dealing with that?
So motion blur is like motion blur. It happens like if it happens for a long time and like let's say several minutes, and if you are not able to detect anything, like first of all, like having an IMU, it helps like even in low feature area, like in our bare eyes, like the example that I gave, like barely like any features in there, but there will be still some features like which we may not see, but our camera might see, like a small dot on the wall or something. So what happens, like there are multiple layers. Like for example, if you have completely no feature, like your blocked camera, in that case, like with your IMU, maybe you will be able to keep track for several seconds, then it will start drifting. So in that case, we have like the health tracker, and in that case, it ends the session and creates a new session and waits for good visibility. And if for a motion blur case, I think most probably what happens, the blur happens for several seconds or so, and like it waits, like if it can recover. If it can recover, then it continues going. But if it cannot recover, then it starts a new session and then merge with the old one. Yeah.
Sorry, yeah, I think you said Orbs Lamp 3, the Orb 3 failed because of memory issues. So are you doing something special regarding memory?
No, we are not doing something special with memory, but the Orbs Lamp problem is I'm not sure how familiar you are with it, but Orbs Lamp module, what it does, like it has for visual automatic, you usually have 3 threads running all together, like mapping, tracking, and loop closing. So what Orbs Lamp does, like it also has a global optimization module after some loop closing. So that actually hurts this performance for very large scale, because global optimization is like, it takes time. So that's why, like if you go beyond, like if you do real-time processing, which we did, the performance was showing for real-time processing, so it hurts the performance. But if we like remove the real-time constant, maybe Orbs Lamp will be able to perform a little bit better.
For you, are you using your own features, or you're using some?
We are using some open source, like we have a lot of feature detector and descriptors, so any of them works, like binary descriptor.
One last question.
Thank you for the presentation. Do you think that your system can work even without omnidirectional cameras?
It's not actually omnidirectional camera. So what we have is actually a front-facing camera, and it has a, I think maybe the like the field of view. The field of view is not even 180 degrees, much lower than that. It's like, I think maybe 90 degree or something.
Should it work with the omni?
Yeah, it would work with omnidirectional camera, and the system is designed like that. Like if you have multiple camera, if you can actually use all of them.
Thank you.
Okay, so thank you once again. And we will meet back again after lunch at 1:30.